Okay, it's top of the noon for me in Pittsburgh, Pennsylvania. My name is Ipek Özkaya. I'm with Carnegie Mellon University Software Engineering Institute, and I'm going to be your session chair today. I'm hoping that many of the attendees will also be here in 2 weeks. So our session is called Machine Learning with and for Software Engineering. However, the papers we have are more in the context of machine learning for software engineering and improving software engineering efforts. We have 6 papers. We're going to present them one by one, and then we're going to dedicate the last half hour or so to conversation and discussion. So I'm hoping you will all take notes and address your questions. We have 1 journal first paper and 5 technical papers. This is a blended session. And our first paper is Lessons Learned on Reproducibility in Machine Learning-Based Android Malware Detection. Nadia Dodi from University of Luxembourg is going to be our presenter. And this was a paper first published in Empirical Software Engineering. Nadia, the floor is yours, and you have 5 minutes of fame.
Thank you so much. Thank you for the presentation. Okay. Can you see my slides?
Yes. Yes.
Thank you.
Want to put them on presentation? Yeah.
So hi everyone, I'm Nadia Dawdi, a doctoral researcher at SMT at the University of Luxembourg, and I will present our paper, Lessons Learned on Reproducibility in Machine Learning-Based Android Malware Detection. This work has been conducted together with Dr. Kevin Alex, Professor Tigawin Dibisyande, and Professor Jacqueline. So as you know, Android is very popular among mobile users since it has maintained the highest market share over the last 10 years. But Android is also a victim of its own success since attackers target Android to spread their malicious applications. To tackle the spread of Android malware, the research community has leveraged machine learning techniques to develop approaches for Android malware detection. Indeed, many approaches are published in the literature, but malware still finds its way to mobile users. And in our study, we aim to assess published work to see why malware is still spreading despite the massive work published in the literature. And in this work, we assess the reproducibility of published work, since the reproducibility is an important criteria for acknowledging a research contribution. So in our paper, we are conducting reproduction, which means, according to ACM terminology, that we are a different team that tries to use the same experimental setup. And I also want to mention that our production study should not be seen as a criticism of the reproduced projects. Actually, being selected in this study means that these approaches already care about open science, since the original authors make some or part of their artifacts publicly available. So to conduct a production study, we need to collect the data set, extract the features, embed them in vectors, and then train the machine learning algorithm for the classification. How our production subjects are selected. So we have considered 16 major venues in software engineering, security, and machine learning. And we have selected the papers that have been published between 2009 and 2019. And after applying our selection criterion, we have ended up with 5 papers that satisfied the minimum criteria for their production attempt. These papers are Dribin, Mamadroid, RevealDroid, DroidCat, and Malscan. So in our paper, we were able to reproduce 1 out of 5 approaches. And also here, the time doesn't allow to go through all the problems we have faced during our production study. So it's not about executing the code and writing down the results. Our production study involves collecting data sets from different sources, which can be really challenging. And even when the code is provided, it needs to be reviewed, debugged, completed, and sometimes even corrected. And that involves a massive guesswork and code rework. Our study has also raised the issue related to the absence of a systematic method for deciding about the success or failure of a reproduction study. And also, when an approach is not reproducible, it cannot undergo irrefutability check. So in our paper, we describe our production journey of 5 approaches on machine learning based Android malware detection. And with our study, we aim that we hope that we all learn lessons from this work and invest more in making our research reproducible. Thank you.
Thank you very much for the very clear presentation, Nadia. As I announced in the beginning, we'll go through all the presentations and then we'll do questions. And there are some interesting insights in the paper that I'm hoping we'll get into it. So our next paper is Deep Analyze Learning to Localize Crashes at Scale. And Manish Shetty from Microsoft is our presenter today. Manish, the stage is yours. Can you share your slides?
Yep, just doing that. Let me know when you can see my slides.
Thank you.
Yes,
we can. Thanks. Hello, everyone. I'm Manish from Microsoft Research, and I'll be talking about our work called Deep Analyze, where we learn to localize crashes at scale. So, in terms of motivation and to just give us some context to go with, today when crashes happen around the world, Microsoft collects crash dumps from systems for root cause analysis and bug fixing back at Microsoft. So a key component of this analysis of crash dumps that helps with this analysis is called Bang Analyze. It's a debugger extension which has been built and maintained over 20 plus years for the 2 decades for automated analysis of millions of crash dumps per day. And it performs various kinds of tasks such as finding the blame frame in a crash stack, fault localization at the thread level, and so on. But over time, there have been certain limitations which have cropped up, and let me just give you a brief of what those are. For example, the code base is quite big and it's become hard to maintain because it's monolithic, and it's become hard to maintain, like I said, over the 2 decades. Also, the code base relies on hundreds of heuristics which have been encoded by domain experts over the 20 plus years. And newer code changes that we have to deploy will take months to do so. And the most important limitation is that new applications which are coming up today we'll have to write new rules and plugins for these new applications to be onboarded onto Bang Analyze. So the question we want to answer is, can we augment Bang Analyze with data-driven approaches and see if that improves the scalability issues that we have here? So in this work, we try to answer that question by proposing Deep Analyze, where we leverage recent advances in deep learning and natural language processing to build a data-driven system. Particularly, we focus on one scenario, which is the data-driven prediction of blame frames in a crash stack. And by blame frame, I mean the frame that most likely caused the crash. And hence, it will lead us to the root cause eventually. So there are specific goals that we want to keep in mind when we design Deep Analyze. And we want to move away from these manually written heuristics and rules. And that would enable us to do analysis for new applications and scenarios with minimal effort and minimal label data as well. So those are the couple of goals that we want to have. So over the talk, I will go through our approach, which begins with a large-scale study of crashes. We get insights and findings from this empirical analysis of crashes, and those insights will guide the design of Deep Analyze. We then build Deep Analyze and evaluate it on real-world crash data. So to go over our empirical analysis briefly in the interest of time, we analyzed 362,000 crashes from various sources. We looked at multiple properties of crash stacks. For example, we looked at crash locations in the crash stack and found that in 33% of cases, the crashed location is deeper than the top frame of the crash, which is technically what people would assume to be the crash location. So therefore, the identification of the crash location or the blame frame is a harder problem than we think it is. And again, in the interest of time, I will skip a couple of other insights, which we can get to in during the discussion session. But one of the key insights that we looked at is how frequently a method is blamed in crashes. And we do so by using a custom metric that we define called blame ratio, which is nothing but the number of stacks where a method is blamed divided by the number of stacks containing that method. And what we find is that a significant fraction of methods have a blame ratio less than 1, indicating that a method blamed in one stack need not be always blamed in another. And therefore, you can't really memorize blame frames and simply predict them. So whatever deep analyze does, it needs to capture some amount of context to make this decision of which is a blame frame and which is not. And this context we get from other methods in the stack above and below every frame. And please refer to our paper for more insights and details from our study. So based on these insights that we gather from our empirical study, we take inspiration from natural language processing and formulate our problem of blame frame prediction as a sequence prediction task. We then build a Bilestium CRF-based model for our task. For more intuition on the design of this model and more details on each layer used, please refer to our paper. To further improve performance on top of our Bilestium CRF model, we use a novel multitask training procedure for training. Here, what we do is we train the model to not just predict the blame frame, but also the high-level cause of the crash or symptom. For example, was it a Stack Overflow? Was it a zero division error? Was it a null pointer error? And learning this jointly along with blame frame prediction vastly improves performance and generalization of our models. Finally, to evaluate deep analyze, we compare against multiple heuristics as well as machine learning-based approaches for crashes from 4 popular applications from Microsoft: Edge, Excel, Word, and Outlook. We observed that although these baselines are quite strong, deep analyze combining context and complementary information using that novel multitask learning procedure outperforms all of these with an average accuracy of 90%. But the question that remains is, how do we scale this to new applications and platforms? Does this mean I have to train a deep analyze model for every single application that comes in the future? The answer is no. And to answer that, we propose a transfer learning approach. Our hypothesis here is that models trained on one set of applications can be transferred to a disjoint set of applications. And this is based on the observation that stacks across applications have quite a few common patterns and generic patterns, which can be learned application agnostic, and thus can be transferred from one application to another. And we evaluate this by training first a global model on crashes from, let's say, X set of applications. We then evaluate this model on crashes from a completely unseen application, say Edge. We find that this global model predicts 80% of these crashes without seeing a single edge crash during training. Moreover, we also find that we can further fine-tune this global model to particular applications. For example, we could fine-tune to Edge with 90% accuracy with just 2,000 fine-tuning examples. So this not only creates a very scalable solution for which uses very minimal label data to fine-tune and get highly accurate models, but it also improves our training costs and gives us more than 10x reductions when compared to like training a deep analyze model from scratch for every application. So to summarize, we developed deep analyze using recent advances in machine learning and NLP for crash localization. We propose a multitask learning model for blame frame prediction and show an effective transfer learning and fine-tuning approach for cross-application crash localization. In the future, we want to expand to cross-platform crash localization, where we transfer models from, let's say, Windows crashes to Linux crashes, for example. And we also want to extend deep analyze to other tasks such as fault localization and bucketization that Bang Analyze performs today, and thus help the developers. Thank you.
Thanks a lot, Manish. And I'll remind the audience, please feel free to write the questions into the chat and I will coordinate them and facilitate while we're done with all the presentations. Our next up, so that we don't lose time, is Mrazul Haq from University of Texas at Dallas, and he'll be presenting Iraba black box energy testing of adaptive neural networks.
Can you see my screen?
Yes.
Okay. So, hi, I'm Mirazul Haq, and I will be presenting our paper, EREBA, Black Box Energy Testing of Adaptive Neural Networks. Our group is from UT Dallas. So, to deploy AI models in edge devices, apart from accuracy, the energy consumption of the models are also needed to be evaluated. Let's take an example. If a machine learning model is has lesser number of parameters, then the energy consumption is very low, but the accuracy is also very low in majority of the tasks. For machine learning models with billions of parameters, the accuracy can be quite high, but it also takes a lot of energy while doing the inference. But for edge devices, we need a model which has a good accuracy but consumes lower energy consumption. Now, how to save energy? So there are basically two type of energy saving mechanism has been proposed. Till you can divide into majorly two types. First thing, we call it a compressed neural network. That means that we have a deep neural network and it will reduce the number of parameters in the neural network. And the other thing is called adaptive neural networks, which is we actually deactivate or activate certain components of the neural network based on the complexity of the input. So we will be targeting mainly on adaptive neural networks or ADNNs in my talk. So as the ADNN's energy consumption is variable based on input, the energy testing of the ADNNs is needed. Because based on that, we propose two type of testing here. One we call is input-based testing, another we call is universal testing. So in the input-based testing, what we do is we check that if a perturbation is added to a meaningful input, small perturbation is added to, so then if the energy consumption of the model goes significantly high or not. The second one is universal testing. In here, we do that we take any kind of input. It can be meaningful or it can be noisy also, and check is the average energy consumption with those inputs is much higher than the meaningful inputs or not. So before going into the energy testing, let's talk about how the accuracy based testing is done on DNNs. So generally we can formulate it as an optimization function which has these components. So main components are two. One is the perturbation that is added to the input, and another is an objective function. So let me tell you, the one thing is till now the majority of the testing scenarios mainly consider input-based testing only. So here that's why they have a separate component for perturbation. So there is a C which is basically defined by the tester. Now the objective function for accuracy-based testing is as something that represents the relation between the input and output of the DNN, more specifically the input and softmax layer of the DNN. But the problem with the energy-based testing is we do not know the relationship between input and energy consumption very clearly. So that we need to define that first. So previously, we have worked on this, and for white box scenario, we proposed an energy testing method called ILFO. So what we found out that for ADNNs, the energy consumption is variable based on the activation or deactivation of the components, and the activation or deactivation is dependent on certain intermediate outputs. Now, if we can use the same optimization function here, but here the objective function is actually dependent on the intermediate outputs rather than depending on the final output itself. So as we are talking about black box setting, so let's talk about how the accuracy-based testing is done on the black box setting. So what the problem with the black box testing is, we do not know the relation between the input and output because the DNN is not accessible by the tester. So the function F become missing. But what we found for accuracy-based testing is like if a test input is created on a certain model, and if we use the similar particular input in a similar model, that test input can also be effective. So because of that reason, we saw that there is transferability exists between the inputs, and a similar model can be used as a surrogate model of the target testing model. So how it works is there is a target model we want to test. We feed inputs to them and we collect the label data. And based on the input and label data, a surrogate model is trained, a similar model. And we use the white box testing scenarios on the surrogate model to create test inputs. However, in our case, we saw that for energy testing, these transferability does not exist. So we cannot use the same method here. So we found out an alternative method. So what we saw that if we plot like graphs of a number of activated components in a ADNN and the energy consumption, this actually shows a stepwise pattern. So that means that if we can find the relationship between input and energy consumption, that means that we can find the relationship between it would be similar to the relationship between input and the number of activated components. Based on that insight, we propose ARIBA. So here we have an adaptive neural networks, ADNN. We feed inputs to that ADNN, and we collect the energy consumption caused during that, during the inference. So here one problem is the recording the energy consumption. So as we this energy consumption measurement can be noisy. So what we do is we measure it multiple times, and we discard the outliers here. And based on the input energy consumption, we train a regression model, and we replace the objective function f with f of EST. So here the thing is f of EST is dependent on the estimated energy consumption here. Now I already discussed that there are two types of testing we have. One is input based. The difference between input based and universal is there is no component of perturbation here. So we are only targeting the objective function for minimization. So here, this is the effectiveness result of ARIBA. So for overall, we have tested in for 2 data sets and 3 ADNNs, and for overall result wise, our method outperforms all the other baseline techniques. Only when the surrogate model based approach only works when the target model and surrogate model is the same ADNN. Otherwise, it does not work well. So this is the results are, and that will be my presentation. Thank you.
Thank you very much. And our 4th paper is from Agnes Chiborowska from Virginia Commonwealth University, and she'll be talking about fast change set-based bug localization with BERT. Agnes, the stage is yours.
Thank you. I hope you can see my screen, and yep. I think we can get started. So hello everyone, my name is Agnieszka, and let's start with fast change set-based bug localization with BERT. So in this paper, we propose a bug localization tool that focuses on 3 things. First, we want to locate bug introducing change sets or commits. Secondly, we want to capture semantics of input documents, and finally, fast retrieval. This essentially means we want to quickly localize relevant change set and minimize the time a developer has to wait for the result. To address those 3 requirements, we propose FBL-BERT. FBL-BERT uses BERT to capture semantics and late interaction architecture that enables efficient retrieval. So how it works? First, the model processes bug report and change sets separately through BERT and creates a matrix for each of the documents. Next, for each word vector in a bug report, we look for the most similar word vector in a change set. Then we sum the cosine similarities between the most similar pairs, and we have our final score. So the 2 main advantages of this approach is that first, it preserves information at the word level, which should help in capturing explicit code tokens if such tokens exist in a bug report. The other thing is that the model is optimized toward maximum similarity of vectors, and this essentially means that we can first find potentially relevant change sets based on whether they have similar word vectors, so that can speed up the retrieval process later on. So in practice, using this model consists of 3 steps. First, of course, we need to train the model. Secondly, we take all our change set and encode them with the trained model. Then we put the encoded change set into an index. Preferably, such index should support efficient vector similarity search. And finally, our last step is retrieval. When a bug report arrives, it is first processed by FBL-BERT, and it produces that matrix. And then we take every word vector from a bug report, and again, we ask the index to give us the most similar word vector in a change set. Our goal here is to find top, let's say, 1,000 good candidate change sets, which already have similar word vectors to our bug reports. And having that, we will now only re-rank our good candidates. So let's briefly look into the results for RQ1. In this table here, we show retrieval accuracy measured with mean reciprocal rank. As our baseline, we use Locus, which is a vector space model. and also two T-BERT models, which are recently proposed deep learning models, also for change set retrieval. The difference between FBL-BERT and T-BERT is that T-BERTs are using document-level representation and FBL-BERT use word-level representation. And overall, we can see that FBL-BERT performs better than Locus and both T-BERT architectures. So the natural question is when that happens. We decided to look into results for different types of bug reports, not localized, partially localized, and fully localized bug reports. So first, looking at the results for not localized and partially localized bugs, we see that all BERT models perform better than Locus, and FBL-BERT brings the highest retrieval accuracy. In the case of fully localized bug reports, we observe that Locus improves, which is expected since this is a VSM model. However, now the performance of T-BERT and also FBL-BERT drops. To get a better understanding why this happens, we did an error analysis, and we observed that very often a bug report that is fully localized contains multiple stack traces or code snippets, which basically means a lot of code tokens. In such situation, FBL-BERT tend to struggle deciding which code token is the most important. All in all, we do see improvement in retrieval accuracy when using FBL-BERT. However, it works best for bug reports that have no or a few localization hints. And let's also look at the time that is required to retrieve a change set. In this figure, we show the retrieval time per one bug report, given different size of a search space. We see here that FBL-BERT, that is marked with squares, retrieve change sets faster than both T-BERT models. Another thing is that while for T-BERT, the retrieval time increases as the search space grows, for FBL-BERT, we can see that the trend line flattens, so it indicates that the model scales up well with respect to growing number of documents. And in the table on the right, we can also see an example of how each of the models scales up depending on the number of documents that we are retrieving from. And that's all. Thank you.
Thank you very much. And without losing any time, I'm losing some of my speakers, maybe not. Next is Tufik Ahmed from University of Colorado, California, Davis. And the paper he is going to present is multilingual training for software engineering. This is an interest as well. So I'm looking, it's kind of is in some of the concerns that we're looking at as well. So I read it with interest, Tufik, looking forward to the presentation.
Okay, thank you. Can you see my screen?
Yes.
Okay, thank you. So today I'm going to present our work, Multilingual Training for Software Engineering. I am Tawfiq. I'm a fourth-year PhD candidate from UC Davis. This work was done by me and my advisor, Professor Prem Kumar Devanbo. Current deep learning models have millions and billions of parameters, and it is really difficult to train such model with limited amount of label data. So in this paper, we propose a novel approach to augmenting the training set. Let's look into the motivation of the work. As you all know, data creation or curation is a slow and effortful process. It always requires some form of human involvement to generate the data for machine learning problems. And we also have seen that for some languages like Ruby, the labeled dataset is less abundant. And for some languages, the data may be more domain specific. We also observed that for many software engineering tasks, the performance of the deep learning model depends on the identifiers. And identifiers are not language specific. It's mostly dependent on the algorithm. So if someone is writing any particular algorithm in multiple languages, there's a high possibility that the developer will use the similar set of identifiers to solve that problem. So inspired from these two ideas, we investigate the potential of multilingual fine-tuning on three popular software engineering tasks. So let me introduce to the task first. So these are the three tasks where we tried multilingual training. The first one, code summarization or code comment synthesis. The second one, code retrieval or code search from natural language description. And the third one, extreme summarization or method name prediction. For all these three tasks, we use CodexGlue dataset, which is a modified version of CodeSearchNet. The data from in CodexGlue comes from 6 different programming languages: Ruby, JavaScript, Java, PHP, Python, and Go. So multilingual training is not new in natural language processing domain. There are several works there. They reported that it is beneficial for low resource languages. And the benefits are observed in two situations: when the languages are low resource and when the languages are related to each other. We have a similar situation here in CodeSleuth dataset. For Ruby and Java, we don't have enough data to train the model properly. And we believe that the languages are related to each other. We will look into some research question on that in the next. So there is advantages of using multilingually trained model. When we are replacing the monolingually trained model, we are actually replacing multiple models with a single one. So it is more practical and easy to deploy. So I have already discussed about the two basic ideas that inspired us for this multilingual training approach. So we have two research questions. The first one: what role do identifiers play in code summarization tasks? We observed that when we abstract out or drop the identifiers from the input, the performance of the deep learning models drops a lot. And on the other hand, when we drop the syntactical token like the keyword operators, the performance does not change that. So from these experiments, we believe that this identifier is playing the most important role in code summarization. And we have another research question: do programs that solve the same problem in different languages tend to use similar identifier names? That means identifier depends on mostly on the algorithm, not the programming language. So please look into our paper for these two research questions if you are interested. So in this slide, I will introduce you to the models and metric we use for these three tasks. For code summarization and code search and method name prediction, mostly we use the CodeButt and GraphCodeButt model. And these are the metrics we use for these three tasks. For code summarization, we use BLEU4. For code search, we use mean reciprocal rank, and for method name prediction, F-score. So all the previous work have mostly used this metric for the evaluation of this task. So this is the result what we achieved from multilingual training in code summarization task. So these two columns represents the performance of monolingually trained model. And we achieved the 17.83 on CodeButt, which is exactly same to the original paper. They also reported 7.83, and we got 18.08 BLEU4 for GraphCodeButt model. So the polyglot CodeButt model achieved 19.06, which is 6.90% more than the previous CodeButt paper. And for the polyglot GraphCodeButt, we got 9.0, which is 5.64% improvement. Note that the improvement are much higher for low resource languages like Ruby and JavaScript. For Ruby, with the CodeButt model, we achieved 17.72%, and for JavaScript, it was 14%. So this slides represents how our multilingually trained model performs compared to the state-of-the-art models during the writing of this paper. And we can see that our multilingually trained model actually doing better compared to the other monolingually trained models. We have tried our task on two separate tasks also, like code search and method name prediction, and we achieved 2.74% improvement with CodeButt and 1.54% improvement with GraphCodeButt. And we have we observe much higher improvement on the method name prediction task, that is 10.09%. So let me summarize the overall contribution of this paper. We showed that identifier name choice is well conserved across different languages. We use Rosetta code, which provides us multiple implementation of the same algorithm. We have also shown that cross-lingual training helps. So you have a smaller data set on Ruby and much larger data set on Python. If you train the model with Python data, that may perform well on Ruby. And the identifier names may matter more in the training data. We have a research question to support this statement. And finally, we presented that multilingual training data improved performance on several tasks. So thank you.
Thank you very much, Tawfik. And last not least, so that we have time for good discussion, is from Rosalina Tufano from University of Della Sverzola Italiana, Switzerland. And she'll be talking about using pre-trained models to boost code review automation. Rosalina,
Yes.
the stage is yours, and I already see your screen.
Okay. I hope you can see the screen. Hello everyone. My name is Rosalia Tufano, and I'm a PhD student at Università della Svizzera Italiana in Lugano. So today I'm going to talk about the work using pre-trained models to boost code review automation, built on top of our previous work towards automating code review activities presented at ICSI 2021, in which, in order to reduce the human effort in the code review process, we made the first step to automate some of its related tasks. Now, we can summarize the code review process in the following way. There is the contributor, who is the developer writing the code and submitting it for review. The code is reviewed by one or more reviewers who can recommend code changes in natural language. And then the contributor revises the code implementing those changes and creates a new version of the submitted code. And this process can be iterated several times until the reviewer is happy with the implemented changes. So we defined two tasks. The first one is the code-to-code task, in which, given the submitted code, we want to automatically generate the revised code. The second one is the code and comment to code task, in which, given the submitted code and the natural language comment of the reviewer, we want to automatically generate the revised code implementing the code changes suggested by the reviewer in the comment. So we trained two transformer models, one for each task, using a dataset that we collected from real code review activities, obtaining for the first task from 3 up to 16% of correct predictions, depending on how many attempts the model is allowed to make, and 12 up to 31% of correct predictions for the second task. Now, these results were promising, but our approach had some limitation, in particular in the dataset that was not really representative of a real scenario. This was due to the fact that, to simplify the learning, we applied some filters that had a considerable impact on the dataset was the one on the length of the method that we set at 100 tokens. So all the methods consisting of more tokens were removed from the dataset. Moreover, to reduce the vocabulary size of the model, we didn't work with the raw source code, but with an abstracted version of it, in which all the identifiers and the literals are replaced with specific numbers, as shown in the example. The problem with the abstraction is that if in the revised method a new variable is introduced, we are not able to go back to the raw source code, and so we removed all the dataset consisting of these cases. So in the current work, we try to overcome these limitations. First, we drop the abstraction process and adopt the byte pair encoding. Here, the goal is to capture subtokens that we can use to construct a completely different sentence. So the vocabulary is built with subtokens instead of entire tokens, and in this way, we can work with the raw source code, and at the same time, we are still able to take under control the vocabulary size. Next, we also relaxed the max length filter. This time, we allow to have in the dataset inputs that have up to 512 tokens. Finally, we also collected the new data from open source projects. In this way, we go from having a dataset consisting of 70,000 instances, to have 167,000 instances. And the dataset not only increased in the size, but also in the complexity. So to handle the new dataset dimension and complexity, we need a more powerful model. So we leave the classic transformer model, adopted the text-to-text transfer transformer, or simply T5, that can be seen as a sort of evolution of the transformer model. So we start the evaluation of the new approach comparing T5 with the ICSI21 model and on the ICSI21 dataset. So we have here the results. In the graph shown, we have on the horizontal axis the beam size, that is the number of prediction the model is allowed to make for a given input, and on the vertical axis the percentage of correct predictions. We can see a noticeable increase in performance, in particular for the code and comment to code task. When the model generates only a single prediction, we have 3 times the chance of getting the correct one. Then we evaluate T5 on the bigger and more complex dataset. and here we have the results, we can notice that the performance of T5 here on the new dataset are lower compared to the performance obtained on the XC21 dataset. But this was something that we expected because, as I said, in the new dataset, we have more complex code changes. So this concludes my presentation. This concludes my presentation. I hope you enjoyed it, and thank you for your attention.
Thank you to all our presenters. At this point, I invite all of them to turn their cameras on because we're going to have an open discussion session. So I would like to first open the floor to the audience. Any questions for any of our authors and presenters? I'm monitoring chat. Well, while you all think, I would like to start my first question and target it to Nadia. I think your results are pretty interesting that you were only able to replicate 1 out of the 5 data sets. So given the challenges you went through and given that experience, and you're in a session with 5 other papers who went through similar kinds of tests, what would your recommendations be to the rest of the authors in terms of improving the reproducibility of their work?
Yes. So based on my experience, the documentation of the tool or of the data set, the process of collecting the data set, because sometimes we conduct experiments on various data sets. We collect data sets from different sources, so we need to keep track of all these sources, and also to clean the repository, because I have, based on my experiment, I got one repository with thousands of scripts, so I needed to guess which script has been used to conduct the experiment. So that was really difficult. So at the end of the experiment, we need to clean the repository and keep only the things that worked. And also, as since we are doing some machine learning experiments, there are some libraries that we can we need to fix the seeds for the experiments to control the randomness of the results, because so this way, the results we are reported in the paper, we are sure that other people can reproduce them exactly. So yeah, that would be it.
Mm-hmm. Okay, I think that's important, because even sometimes within the same research team, if somebody wants to repeat it a couple years down, some of the assumptions may not hold. And I think we overlook the kinds of assumptions we make and which ones need to be communicated for improving reproducibility of the results.
Yes, and sorry, and to add, in other domains, not in software engineering or in malware detection, but in other fields, some researchers fail to reproduce even their own work. And that's really surprising. So, the reproducibility is something very important that we need to invest more in making our research reproducible.
As someone who's been humbled by that, I really recommend everyone to try reproducing your own results with different set of researchers within even a 6 month. All right, we have a question for Tufuk, and the question reads: did you consider evaluating multilingual model performance on a translation task?
So, yeah, get it right that the translation means code translation. That means Java to Python or Python to Java. If this is the problem, I would say we have not tried this multilingual training model on translation tasks, but I believe that if the target language is the same, then this multilingual training will help. That means if we have a data set from Java to Python and JavaScript to Python, then this multilingual training should increase the performance compared to monolingually trained model. Thank you.
Thank you. So my next question is targeted to all the 5 authors who have demonstrated incredible quantifiable work and experimentation. However, none of the papers included how does this make it into the hands of the developers, and how does it change the developers' day-to-day task. So I would like each one of you to reflect on that, and whichever one of you would like to start can get started, and then we can take turns. If not, I'm happy to volunteer one of you. Manish, maybe I'll volunteer you because you come from a developer environment and your data is from a very intensive developer environment. How did it make it into the hands of any of the products that you mentioned, or will it? What are the paths to make these work to really change the developer tasks, which is the goal at the end of the day?
Yeah, a good point. And let me be clear, like the whole, I think our paper and our project is kind of motivated from the developer perspective. The whole problem was that, like, if you think about what I explained, there's already a system which has been working well for 20 years, and so why do we have to touch it, right? But the problem here is that tomorrow, when let's say a new application comes or something new comes up, some new environment comes up, we've actually did kind of a short kind of interview session with multiple developers who actually code and write the heuristics into this system, and they are really like sad about the fact that they have to keep writing these rules and keep trying to maintain this 20-plus-year-old like monolithic big thing, right? So in that sense, we actually have got good responses from our own developers saying this is going to help them a lot, especially to just start off a new application and Microsoft is going to come up with new products every single year for sure. So having something which is this scalable and like gives you a quick way to like onboard and like start looking at your crashes and improve your software is something that all the developers are like really appreciating. And in terms of whether or not it's made into a product, it's actually got deployed very recently. So happy to share that as well.
Yep. All right. Any other insights from any of the other authors, presenters? No. Well, I encourage you all to think about it, because to demonstrate quantifiable outcomes on experimentation on test data is one thing, reproducing is another thing, but how does it really make an impact on a developer? What is that path is, I think, important in terms of being able to improve some of the work. So,
one thing, yeah.
Go ahead,
so one thing I would say that for my work, it's not directly related to the developer, but it's more related to the machine learning engineer's perspective, because like till now the evaluation of machine learning systems is basically dependent on how accurate that system can be. But it's like for many of the tasks we saw that, for example, machine translation tasks, even for code generation, code summarization, if the summary of the code is very long, then it's not very fast. It will take more energy. It will take more energy to like process those code summarization tasks. So in terms of should be a like evaluation on terms of time consumption or energy consumption on these kind of model also. And the more compact the output can be, or the more compact the energy consumption can be, that would be more useful for the world itself in terms of green AI, I would say, or I mean, even for it would be very helpful for the like developers also, like if they can get a shorter time, they can get a response in a very shorter time. So that would be definitely helpful if the energy is also tested.
That's exactly the point. All of these numeric results are impressive and it's exciting. However, what does it mean in terms of, even if I'm not using the tools, what insight do I have in terms of like, if it's a very long code summarization, don't even bother, because the trade-off will not make it at the end. I use this tool to localize my bugs, hence I'm able to find the bugs quicker. Is it maybe in the background to my code, or is it really part of the developer? Is it obvious to the developer, and are they aware how they are able to interact with those? So those are, I think, important, while not in the scope, but I think it helps it improves the understandability of the work, at least for those who are not in the trenches suffering like Nadia did in terms of understanding which scripts were they really learning on. Thank you. We have a couple of audience questions and I want to make sure that we get to them. This is from Prem Devenbu to Rosalina. The question is, do you know why the code T5 performance declined for the bigger new data set?
Yes, thank you for the question. I don't know exactly what do you mean with the code T5, but about the general question, Yeah, we associated this decline of the performance to the fact that in the new data set, it is bigger, but also the instances, so the methods are bigger, and so they are more complex. So we can also have more complex code changes. So this is the reason that we associated to this decline.
Okay. Next question is from Agnes to Manish. How does your deep learning approach compare to heuristics crafted specifically for each application? Are heuristics better? It's a good question.
Yeah, good question. And to clarify, I think the way we learn these deep learning models are actually labeled data from these heuristics. So what we use as ground truth is actually the labeled data that we get from the system that we've been using for 20 years. So in that sense, like the best thing, that is the 100% accurate thing, is the heuristic. So we do believe that heuristics itself are the best. And what we're trying to solve here is not to improve the accuracy of these heuristics, it's to just get rid of them completely. Yeah.
And another question for Tufik. Do you think BLEU is a reasonable metric for BLEU, is a reasonable metric for evaluating code summarization? If not, is there a better metric that we can use?
So personally, I don't believe BLEU is the most reasonable metric for evaluating the code summarization task, but right now we don't have other better alternative to this metric. It was found that BLEU is highly correlated with human subject studies. It's found that it is highly correlated with the human perception, but this is not a perfect metric. And it's if you make the prediction is slightly changed from the original one, like set the value, and the prediction is sets the value, you will see that this metric will heavily penalize the prediction. But semantically, that is right. There are recent work there which is trying to do some semantic similarity to find to introduce a new metric for or this kind of summarization task, but I think still now BLEU is the most popular one, and until we have a better metric, we need to stick to it. That's it. Thank you.
I would like to challenge that perspective, but we don't have enough time. Until we have a better, we rely on it, or do we spend more time trying to find the better metrics? Because I think the software engineering research have suffered enough in terms of feeding the metrics beast, especially in all the areas of the work that we're talking about. And now we're up against these machine learning algorithms, which have all sorts of uncertainty around them. So, but I will leave it at that. Thank God we have only 7 minutes, and I want to ask a question to Agnes. Agnes, so with the bug localization and evolution of the changes that are going through, one of the what would you recommend in terms of how would a developer needs to incorporate? Again, it's the kind of a same question, but especially in terms of locating the bugs and being able to resolve them. What were some of the insights that you think a developer might take into, even if they're not using some of the approaches that you talked about in your paper?
Okay, so considering we are dealing with change set, basically what we saw is that if you have a bug report that already mentions classes, investigate the classes. That's the easiest way to find it. If you want help, probably investigate repository history to find developer that last touched that class, and then you may find some help, definitely. We saw that the biggest problem, both for developers but also for the models as well, is dealing with bug reports that are very general in the description. So mostly natural language type of a bug report, sometimes reported by a user with a very vague description of a problem. For that, I think the experience is the best answer for developers. Mm-hmm. We did see improvement because we are dealing with supervised learning, so the model can help for such a scenario. But for a situation when this is something completely new, even a best machine learning model may fail because it's something that has not yet been seen during the training. So I would say experience and proper examination of the content of a bug report.
Thank you. And I think the audience is able to unmute themselves and contribute to the discussion as well. My last question is more of a philosophical question to the presenters, but as well as to all of us who are now going through the excitement of, okay, we have machine learning, let's improve the software engineering and software development efficiency. I don't recall which one it was. Let me go back to your notes, but I think it was Tufuk who said, do we need to train a new model every time we have a new code base, or do we need to go through these? So how much are these machine learning approaches are going to really help us, or are we really overly excited with the potential? We have the data, we have these algorithms, let's try to look into them. So what does the future look like, and what is the good work in this area? So this is for anyone, and if nobody's taking it today, maybe it's food for thought for future. Nobody believes this is going to change how software engineers do development. That's sad.
So one thing I can say that there are works that is going on that how to like decrease the training time of the neural networks. So if that happens, even if the training time can become very low, then training new models for new software database, that won't be problem in future. But one thing that would be problematic in terms of machine learning is of the explainability of the machine learning, because like until unless we get a proper explainable models, not only like what we say, it's like explainability. I mean, it's a proper like that cannot be attacked. I would say it's very difficult to create a system that cannot be attacked, but still is something that is less prone to attack. And then till then we need to improve the systems in terms of usability.
Mm-hmm. So I think there are exciting new features and functionality coming from, I think some of this is in the code summarization, code review, the Copilot tool sets that are coming out. Those are all taking advantage of the machine learning approaches. But I think we as software engineering researchers have also, I think, the responsibility of asking the question in terms of, okay, what does it mean to really put this in practice beyond providing the experimentation, and what does that path look like? So I think I'm going to leave all of us with that, unless there are any other questions. I enjoyed reading all the papers, and I encourage all the audience to go read the papers. There's really good work in there. And then I encourage all the 5 of the authors read Nadia's paper and see how it might be replicated. So this was a very nice bundle for this session. Any last questions, last takers? Not? Thank you very much. And I'm hoping to see some of you in 2 weeks in Pittsburgh, and the rest of you in other sessions. Bye.
Thank you.
Thank you.
Thank you. Yeah.